Okay, hello everyone, welcome back to the 18th lecture of Introduction to Stable Homotopy Theory. And today we'll finish the story of Bouts-field localizations and perhaps start the story about Thom spectra. We'll see. I also would like to give a very sketchy description of chromatic homotopy theory, if I can. Today will be, perhaps this first part will be a bit more sketchy than usual because I won't be able to prove everything, but I want to give you at least a flavor of how the theory goes. How do you decompose further this P-complete homotopy theory? And it's an example that we can actually work out in some detail. The goal is to compute LKU of a spectrum X. In particular, the first step, and the main step actually, but we will get more information in the process of doing this, is as to prove that this is a machine localization. It's obtained by tensoring LKU of S by X. And then also give a description, explicit description of LKU of S. I'll write it as a pullback of some spectra that are quite explicit, actually. And okay, to do so, we will use the arithmetic fracture square that we described last time. So our goal, the steps are describing LKUX rational and LKUX P complete for every P. And the first one is actually quite easy. So I'll write it as a general statement. So the lemma is let E be a spectrum such that its rationalization is non-zero, or if you want, such that there is some non-torsion element in its homotopy groups. And then for any spectrum X, we have that the rationalization of the E localization is equivalent to just the rationalization. Or if you want, i.e. the map X goes to LEX is a rational equivalence. So the rational part is easy, as I often recall. You just literally, you just give what its rational homotopy groups are and you know everything. Okay. So the proof is easy. So let A be the fiber of this map. This is E acyclic. We need to prove it is Q acyclic. That's all that we need to prove, literally. So we know that E tensor A is 0. Therefore, its rationalization is 0. So far, so good. But remember, rationalizing is as machine localization. So that's the same thing as tensoring by EQ is 0. And now, and EQ is just a sum, of shifted copies of HQ. We had a more canonical description as sum of the shifted argument plane spectra of the rationalized homotopy groups, but of course that doesn't matter, and that's non-zero by hypothesis. So EQ tensor A is 0 if and only if HQ tensor A is 0, and that's the end of the proof. And of course, we used that EQ is non-zero for this implication to show that there is at least one HQ sum under that. Because if EQ is 0, then this, of course, doesn't work. Okay, so the rational part is easy. Let's see what we can say about the p-complete part. The p-complete part is where the interesting things happen. So let's see. I wrote this. Okay. I didn't finish writing the proof in the notes. Okay, well, let's improvise. It's not a hard theorem. Anyway, so let E be a spectrum, any spectrum, and okay, X another spectrum. But then you take the E localization of X and you p-complete, and that's the same thing as the E mod B localization of X. So that gives us a description of the p-completion in terms of another Bousfield localization. And actually, let me prove first an additional lemma that we need in the proof of this lemma. So let, okay, E be a spectrum, E actually spectra. So then the p-completion of X is E local if and only if X mod B is E local. And the proof is actually easy. So remember, we had a fiber sequence. S mod P goes to S mod P to the n plus 1, n, say S mod P to the n minus 1. Oh, sorry. Before I say this, I should say that one implication is clear. Since X mod P is the p-completion mod P, this is clear. Sorry, forgot to mention that. So now we need to do the other implication. So remember, we have a fiber sequence. So we get a fiber sequence like this. Therefore, if X mod P is E local, then X mod P to the n is E local for every n. That's by induction on n and using that E local spectra are closed under extensions. But then the p-completion, which we have seen to be the limit of X mod P to the n, is E local, since E local spectra are closed under limits. Actually, let me move these statements downstairs, since it's going to be helpful to have it here. Put it this way. Okay. And let's prove this lemma now. So if we have a spectrum, okay, so okay. So the map X goes to LEXP complete is an E mod P equivalence, because you can factor it as first you go to LE and then to its P completion. And this is an E equivalence and therefore an E mod P equivalence, because if you have an E acyclic spectrum, you can tensor it by E mod P and you get 0. So it's E acyclic, and that's an S mod P equivalence for the same reason. If you have something that's 0 after tensoring by S mod P, it's 0 also when tensoring by E mod P, because it factors as. So the only matter is to show that that guy is E mod P local. And so note that by the lemma, the previous lemma, EXP is E local. Because if you take it mod P, that's the same thing as L of X mod P, which is E local. So, okay. So now let A E mod P local. This means exactly that E tensor A mod P is 0. Therefore, maps E tensor A mod P into this guy, which, sorry, E mod P acyclic, not local. Remember, this guy is, sorry, not E, tensor A mod P. So this guy is E local. I'm making a mess. So, okay, let me say it differently. Okay, let A is E mod P acyclic. Therefore, E tensor A mod P is 0. Therefore, A mod P is E acyclic. And therefore, the mapping spectrum from A mod P to this P completed LEX is 0. Therefore, multiplication by P from the mapping spectrum from A to this guy is an equivalence. But this guy is also P complete. Because, well, you can write it as limits over n of maps A, LEX mod P to the n. And then you can bring it, the n outside. In general, mapping into a P-complete guy always gives you something P-complete with this argument. Okay, we have a P-complete spectrum where P acts invertibly. Well, therefore this guy is 0. As we wanted. Again, this is a bit of a bunch of tricks you can probably guess. how these things go on your own, but yeah. Questions?
Excuse me, this is probably a very basic question, but why does p-completion commutes with this mapping thing on the second variable? I mean, why can you put the limit outside?
No, the limit outside you can always put. The magic is I can put this fraction outside, actually. Map A blank is a right adjoint. So I can always pull limits out. What's the difference with Boolean groups is that now I can also put the quotient outside, because right adjoints commute with cofibers, which is a consequence of stability.
Okay.
These cofiber sequences are the same thing as fiber sequences.
Okay, great, thanks.
So that's why this doesn't work for abelian groups, but it works for spectra, and it works also in the derived category of abelian groups, of course. Okay. Okay, so summing up, we have a pullback square. Here we have the KU localization of X going to the rationalization of X here, and here you go over PLKU mod PX, and then the adelic part, which again is completely determined by their homotopy groups, so that's not that bad. Our goal now is to understand LKU mod PX. And here I'm going to have to bring some actual computations. So I'll need the existence of two maps. One of them, you should have at least hinted at it in the exercise session, but I'll mention it again. And the other is, well, is sort of an important object, but okay. So we need the following facts. So fact one, there exists a map of rings, of ring spectra, and so far in this class I've only defined homotopy ring spectra, so you can think a map of homotopy ring spectra, but in fact it's even a map of infinity ring spectra if you have this definition. Psi r from KU P to the P completion, KU to P completion of KU for every R coprime with P. Now, if I understand correctly, in the exercise session, you've seen the existence of these at the level of spaces, and Pavel has said that it doesn't deloop to KU, which is absolutely true, but it does deloop if to the P completion if R is coprime with P. And in fact, this gives an action of the profinite group ZP cross on KUP, but we don't need it. I'm just mentioning because, well, because it's important. And then we need, and then this fact one is actually not that hard to construct. You've already done it at the level of spaces. With a little bit of effort, you can upgrade it to a map of spectra and see that some map of homotopy ring spectra is. It's not hard. I'm just not doing it for lack of time, but this could do. The second part is harder. So there exists, and here I'll write stuff for P odd and then explain how to modify it for P equals 2, because unfortunately that's P equals 2 is kind of special in this story. So there exists a map V1 from sigma 2p minus 1 of S mod p to itself. And here I'm saying v1 to the, I'm going to call it v1 to the fourth from sigma 8 S mod 2 S mod 2, which is a KU equivalence. And this is harder to construct, so let me tell you briefly where this comes from. So V1 is constructed so that it fits in a diagram. So here I have, so S2p minus 1, S p, and here you can consider the boundary map of the sequence defining S mod p. Here you can actually consider just the projection mod p. Here there is a map alpha p, where alpha p lives in pi 2p minus 3 of the sphere and is the smallest element. Sorry, it's the element in smallest degree. Of order p. So it's the smallest piece of p torsion in the homotopy groups of spheres. And of course, I would need to prove that such alpha p exists and that this factorization also exists, and that this factorization implies that V1 is a map, it's an equivalence on KU. A reference for this, by the way, is Adam's paper on the groups JX4. Don't be too afraid that it's the fourth paper in a series. It's kind of standalone. You can read it pretty much on its own. But I shouldn't misspell Adam's name. Poor guy. And again, this is also not super hard. In one lecture, I think I could do it. But for the sake of brevity, I'm going to skip it because I'm going to need a third fact, and that is I definitely couldn't do it in one lecture. But let's put together fact 1 and fact 2 and see what this gives us. So we have, since psi r from KUP to KUP is a map of rings, there exists a null homotopy of the composition from the sphere to KUP to KUP complete psi r minus 1. This is just saying that psi r composed with the unit is homotopic to the unit. That's a particular consequence of psi r being a map of rings. Therefore, a null homotopy. And actually, since the target is, the fiber of the target is P complete, I can as well P complete on the source. And therefore, a null homotopy of S mod P, KU mod P, KU mod P. But I'm going to keep calling this map psi r minus 1, even if S mod P is not a ring anymore. Careful, but I can still take the sequence above and take mod P. That's still allowed. Okay. But now all these maps, this null homotopic sequence, or actually this, let me say this fragment at least, oh, sorry, 2p minus 1, gets a multiplication by V1 map and these commutes. And this is an equivalence because V1 was a KU equivalence. And also this fits, of course. This other piece of the sequence. So long story short, if we define S mod P with V1 inverted as the colimit of this thing, so I think I need to put a minus here. So I'm taking essentially the formal, I'm formally inverting V1 and the homotopy of S mod P. We get a map S mod P like this, KU mod P, KU mod P, psi r minus 1, and we still have a null homotopy of the composition, since this is a colimit of sequences equipped with a null homotopy. So we get a sequence. So I give you two maps and a null homotopy of the composition. And now this is fact 3, which is really hard. It's a hard computation. This is a fiber sequence. And okay, actually, I should perhaps say a couple of things about how you fix this for p equals 2. For p equals 2, you get a map. Well, you invert v1 to the fourth. It's the same. Well, okay, let's write it like this. But here you have to put KO. You have to put the real piece instead of KU. It doesn't matter, but it's a bit annoying in this setting. Okay. In fact, 3 is actually very related to the computation of the image of J that Pavel might have explained a bit in the exercise session. The idea is, well, the homotopy groups of this fiber are easy to compute, and the computation of the image of J actually can be put by showing that the map from these to the fiber of these is a surjection of homotopy groups. And then you do some really hard computations and you show that these spectrum here and the fiber of these have the same cardinality in homotopy. So if you have a surjection between two groups with the same cardinality, then it is an isomorphism. And that's hard. I be honest, I do not understand the full computation, even if I read it a couple of times. It's quite hard. And this was done actually. So the computation was Adams and Baird. And maybe I should also put the name Miller here. And the observation that this computation proves this result is due to Bausfield.
Okay, sorry, I'm a little lost. So why do I get that this, if you scroll up this composition from SP completed, yeah, that this composition is null homotopic?
Well, psi r is a map of rings. In particular, the following diagram commutes. Yeah.
Okay. It's a map of rings, and this is the unit inclusion.
Yes, exactly.
Okay, I did not get this. Okay, thank you.
Write it here. So as I said, fact 1 and fact 2 take a while but are not super hard. Fact 3 is significantly harder, and I'd be lying if I said I understand the complete proof. If someone has a very nice way of thinking of this proof, I would love to hear it. But there are also, I mean, we will see in a second that there are deeper reasons for fact 3 to be harder than fact 1 and fact 2. There are higher analogs of fact 1 and fact 2, but the higher analog of fact 3 is an open conjecture. And people believe it to be false, actually. So it's when you start learning the theory, you realize that fact 3 is of a different nature than fact 1 and fact 2. But okay, with this, armed with this, now we can remark. Oh, there is a remark I should have done like 2 weeks ago that I forgot to do, and I need it now. So let me put it here. So remark, if E is a homotopy ring spectrum, which is a monoid, I call it a monoid in the homotopy category of spectra, and M is a module over E in the homotopy category of spectra. That is, you have maps E tensor M to M that are associative up to homotopy, and what I'll need actually is that this composite here, sorry, where the first is the unit, is the identity. Then M is E local. In particular, E itself is E local, which is not true in general. So this might be a bit surprising, perhaps, for people. But for basically all the localizations we consider, this is going to be the case, because we are going to localize more often than not at homotopy ring spectra. So the proof is, so let A be acyclic, then map A comma M is a retract of map E tensor A comma M, which is 0. And that's because you can get a map and this map comes from a precomposition with the unit of E. You have a map A. Ooh, why am I doing this? No. Am I doing this the right way? Yes. Okay. You precompose with the unit of it. And here you can just tensor by E by functoriality and then multiply. No. Wait 1 second. No, I'm doing it in the wrong direction. You have a map from A to M. You go to a map from E tensor A, E tensor M, and you go, and now you multiply on M, of course. And the composition of these two guys is the identity. And so where mu is this multiplication map. So sorry, why do I need this remark? Because I needed to know that KU is KU local. Otherwise, I wouldn't know how to do these things. In particular, that KU mod P is KU local. Because therefore, KU mod P is KU local. And so from fact 3, we get S mod P with V1 inverted is KU local. Therefore, S mod P V1 inverted is the KU localization of S mod P. And that's the important fact. It's actually quite easy to show that S mod P and S mod P with V1 inverted have the same KU localization because V1 is a KU equivalence. But the key important fact is this fact here. Is KU local. And okay, more generally, you can take X mod P with V1 inverted, and this is going to be LKU of X mod P. Because the left-hand side is the fiber of a map KU mod P tensor X to KU mod P tensor X. And so KU local. So we can put it this. And this is one of the equivalent forms of the telescope conjecture, but I'm going to reserve that name for the statement I'm going to prove now. Although you will see that it's an immediate consequence of this fact. And okay, so this is corollary, which is the telescope conjecture in height 1. Let Ex be a spectrum. Then X is KU local if and only if for every P prime the map V1 from sigma to P minus 2 of X mod P to X mod P, or V1 to the 4th from sigma 8 X mod 2 to X mod 2 for the P equals 2 case is an equivalence. So that's well, that's a very interesting statement. This involves this connects being KU local with some kind of periodicity on X. In fact, in particular, note that if X is KU local, the homotopy groups of X mod P are periodic, because there is this multiplication by V1 with period 2P minus 2. And in fact, we have the homotopy groups, the mod P homotopy groups of the KU localization are exactly the homotopy groups of P with V1 inverted. That's a consequence actually of the fact that I claimed before. that the KU localization of X is X mod P is X mod P with V1 inverted. So the LKU U sees the V1 periodic part of mod P homotopy groups. And by the way, I'm saying it for the homotopy groups, but of course it's true for homology groups for any homology theory. So for example, mod P homology of X is going to be V1 periodic. Okay. Questions about this statement before I prove it? No. Okay, good. So, proof. Well, okay, V1 is a KU equivalence. So, if X is KU local, V1 P minus 1 is an equivalence for every P. So that's easy. Because the fiber is acyclic and KU local. Therefore, good. Okay, so good. So the problem is the other direction. But we know that LKU of X mod P is X mod P with V1 inverted. So if V1 is an equivalence, we have X mod P is KU local. Therefore, by the lemma we have seen, the P completion of X is KU local. And XQ is also KU local by that lemma we have seen, and so X is KU local. Okay, so we say SQ and also the adelic part, which is rational, is KU local. And this guy is KU local. That's because they're rational. Rational spectra we have seen are always KU local. So this periodicity statement allows us to give us a very clean characterization of KU local spectra in terms of some kind of periodicity on the mod P homotopy groups. And well, that's the beginning of a very important story on which I'll say a couple of things. But as a further corollary, let me say that LKUX is LKU sphere tensor X, i.e. LKU is smashing. And why this is a corollary? So first, note that X goes to LES tensor X is always an E equivalence for every E. So the only thing we need to prove is that the right-hand side is local in our case. And that's because I know the fiber is obtained by X tensor some E acyclic spectrum. And so it's E acyclic. But now we have a very convenient criterion to check when stuff is KU local. So we need to check V1 from 2p minus 1 LKU tensor X mod P LKU tensor X. LKU tensor X mod P is an equivalence. But now, well, we know who this guy is. This guy is exactly S mod P with V1 inverted. And this is obviously this is an equivalence by definition. As you can see, constructed once you have fact 3, this theorem is very, very easy. And actually, it would follow only by knowing that S mod P with V1 inverted is KU local. If someone were able to prove it by other means, that would be enough. But I don't know of any proof that doesn't pass through that fiber sequence. And I'm very skeptical that it would exist, honestly. Okay, so we almost have a complete description of KU localization. We just need to understand the KU localization of the sphere. And I'm going to use the arithmetic pullback square. So to understand LKUS, it's enough to understand LKUS P completed. But thankfully, we have a very simple description now of this guy that allows us to compute all its homotopy groups actually in a very explicit and concrete fashion. So recall, we have a sequence by which I mean a pair of composable maps plus a null homotopy of their composition, S KU P complete psi R minus 1 P KU P complete. And the fiber in particular is both KU local and P complete. So, I recall this was LKU mod P of the sphere, by the way. So we get a sequence and we claim this is a fiber sequence. Why is that? Well, everything inside is P complete. Indeed, everything is P complete. So it's enough to check it's a fiber sequence. Mod P. But mod P, well, but this was the fiber sequence constructed using fact 3. So actually, let me give a name to this thing. Let me call JP to be the fiber of KU mod P psi. Oh, sorry. Haha. No one asked me an important question. I keep writing psi r, but this is clearly not true for every r. For example, for r equals to 0, it's obviously false. So someone should have asked me which r do I pick for this, for fact 3. Sorry, I forgot to mention it. So let me go back to fact 3 and just say, well, I could say that there exists an r. And this is a fiber sequence, but for r, topological generator of ZP cross. ZP cross is a procyclic group, so you can pick. Or if you want, it's the same thing as saying that R is a multiplicative generator of Z mod P to the N cross for every N. And what goes wrong for P equals 2 is exactly that Z2 cross is not procyclic. Or if you want, the Z mod 2 to the N is not cyclic, which you might or might not have done many years ago in a first algebra class. So you have to pass through KO that sort of takes care of the spurious Z mod 2 factor in Z2 cross. Sorry, I forgot to mention it. Of course, you need to choose a particularly good R. I think R equals 3 is good, mod 2 or something like that. I don't remember. And there are formulas you can look. It's a purely arithmetic invariant. But anyway, I have this ZP. And for those of you that are curious, this is exactly the homotopy fixed point by the action of ZP cross. And by the way, this is true also for P equals 2. It's just that the homotopy fixed point, since it's not cyclic, it's not computed just by taking the fixed point of a generator anymore. Okay, and so summing it up, you get that this guy is a pullback. And this gives us as complete a description as you can hope. Since psi r, it's easy to figure out its action on homotopy groups. It's actually multiplication by r to the 2n in degree, r to the n, sorry, in degree 2n. You can actually compute the homotopy groups of everything inside, get a long exact sequence, and get the homotopy groups of these. And I just mentioned a following remark for those of you that have seen the story about the image of J in the exercise session. The map pi star of S to pi star of these KU local homotopy groups is the projection onto the image of J for star greater or equal than 1, where J is a certain homomorphism from pi star of O to pi star of S. And its image, it's not injective, but its image is a summand of pi star of S. And the splitting is given exactly by this. And it's a summand, sorry, for star greater or equal than 1. So that's why this LKUS spectrum is sometimes called also the non-connective image of J spectrum. And that's also why these are the P-complete image of J spectrum. That's why they're called JP. And there is more I could say about this, but I prefer to stop here for this. And I want to just give an idea of how this story can be generalized to understand deeper and deeper information in the pi star of the sphere. But first, are there questions about this? So what happened is that people developed essentially this story. It culminated in work by Bausfield, Adams Baird, Miller, etc., as I mentioned before. And people start asking, okay, that's cool. Can we do this thing further? So the idea was, okay, we have understood a piece of the P-complete homotopy theory. So, but can we look at Bausfield localization at S mod P comma V1, by which I mean the cofiber V1 So because we understand completely the part that what happens when V1 is inverted. So now our next step is probably look at what happens when V1 is completed. And can we go further? Can we find a V2 perhaps that gives us an interesting periodic part when you invert it and then you complete and you go further. And you can indeed, but to understand what's going on, it's better to mention a little bit what's the arithmetic data that's controlling this story. So I have to mention there exists a spectrum called MU, which actually we will define at the very beginning of the next topic. Well, it's a special case of a Thom spectrum. We'll define Thom spectra, and so in particular also MU. That is the universal spectrum with a theory of Chern classes. If you've never seen Chern classes, it doesn't matter. It's just I'm just mentioning it for people that have seen them. I will say stuff about orientability and etc. later. But such stuff exists. And pi star of mu is particularly easy to understand. So you can write it as an infinite polynomial ring with ai in degree 2i, but that's not actually a very useful description. I mean, no, it is useful, but it's not a very conceptual description. It's better to understand it in terms of formal group laws. So definition, so R ring, a formal group law is a power series F in x1, x2 that behaves sort of like the Taylor expansion of a group operation at 0. So such that, well, okay, it's technically commutative and one-dimensional. So let me put the commutativity here. Fx comma 0 is x, x0 comma x is x, and then I need some kind of associativity condition. And that's it. Invertibility is forced by the inverse function theorem. Oh, sorry, no. No, yeah. Invertibility is forced by the inverse function theorem here. So, so it's good. And well, for those of you that know what churn classes are, the behavior of the churn classes on mu equips pi star mu with a formal group law, but it's even better. So okay, let me say that the Lazard ring L is the ring with the universal ring with a formal group law. And it's you can define it. You can just take L is defined as Z with Cij for that are the coefficients are from a group law modulo whatever relations you need, so that f of x comma y sum Cij xi yj is a formal group law. You can just write it down. It's just a purely algebraic gadget. And the theorem is that pi star of mu, actually, sorry, I should attribute some theorem by Quillen, which is the magic thing that makes everything work, is that pi star of mu is equivalent to L. And why did I do that? When did I say that? It's because by identifying a mu with L, we can identify some special elements in a mu, which I'll call Vi. So, okay. Questions so far about this definition? No? Okay, that's good. So if we define multiplication by P is a power series in only one variable, Px is just f of x. P factors. It's, multiplication by P. Not very surprisingly, perhaps. And I'm going to need these to define inductively. So multiplication by P, you can see it by the hypothesis, is Px plus higher terms. Actually, P plus higher terms. That's an easy proof. You can do it. And so we can use it to define some elements. Sorry, is there a question? No, apparently. Called Vn. So we define inductively V0 is P. And then in in L mod V0 Vn minus 1, multiplication by P is of the form of some element Vn times x to the P to the n plus higher order terms. So this is Vn is really an element of L mod V0 Vn minus 1. And Vn is a non-zero divisor. There. Nothing of this is really hard to prove. It takes a while. It's a bit of algebraic manipulations with formal group laws, and note that also, even if it's not in a notation, Vn depends from P. Okay. So we have these elements. We have V0 in pi star of mu, which is L. We have V1 in pi star of mu mod P. We have V2 in pi star of mu mod p comma v1, etc. You have this sequence of elements. Oh, and maybe I should say that vi is in degree 2 by I minus 1. That you can just deduce it from this formula. But deduce from this formula and the fact that the degree of the indeterminate is actually minus 2. And in the identification between pi star of mu1 and L. Okay. So that's what happens. So now we have our elements Vn, and I can actually define some, this is, let me put some tildes, since these are not quite the spectra that are usually called En, although they have the same Gauss field localization, they induce the same Gauss field localization. So for our purposes, it's okay. It's going to define these mu mod p Vn minus 1. No, sorry. Mod Vn plus 1, I need to kill all the one greater than Vn, and then I invert Vn. And we define Ln is the localization of these guys here. And similarly, I can take Kn tilde. Again, I'm putting a tilde because they're not quite the things that are normally called En and Kn. In fact, these guys with the tilde decompose as direct sums of pieces that are simpler, which are what are usually called En and Kn. But this is En tilde modulo V0 Vn minus 1.
Excuse me, I have a formal question.
Yes?
So, do you make any choices to divide by Vn plus 1 without dividing by V1 and previous ones?
You're absolutely right. You have to make a choice here.
Okay, thanks.
There is a canonical way of constructing this Ln that doesn't make any choice, actually. But for the sake of giving a short argument here, I'm just making choices. And sorry, and Lkn is this L to Kn tilde. Kn tilde is a sum of many, many copies of another spectrum called Kn. And that's what these guys are called. And okay, I have 15 minutes, so how much do I want to say about this? So first of all, there is, and this is actually easy to prove using the same techniques I used so far. It's the chromatic fracture square. You can, for every spectrum X, there exists a pullback square. Lnx, Lknx goes to Ln minus 1x. And let me get this right, Ln minus 1, Lknx. So you can inductively build Ln by all the Lkns plus gluing data. Okay, and that's actually not hard. I think you could do with what I said so far. Just check that every Kn local spectrum is En. No. Yeah, that every Kn local spectrum is En local, and every Kn local spectrum is En minus 1 acyclic, and plus a couple more verification, then this follows formally, as we prove the arithmetic fracture square. And then there is this theorem which is actually not that easy theorem at all, which is the chromatic convergence theorem. Which is if X is a finite spectrum, now it's important. It's false for general spectra, but it's true, for example, for the sphere spectrum. X is the same thing as the limit of its En localizations. Sorry, not X. It's P completion, of course. Everything in the chromatic fractal square is P complete, so you cannot hope to recover more than the P completion. But and what else do I want to say? I want to say what these VIs show up and what the telescope conjecture has to do. So turns out that so for every n there exists, so I'm going to describe an inductive procedure. So I'm going to tell you we can construct something that's called S V0 to the I0, Vn minus Vn, sorry, to the In, which is just a finite spectrum. In fact, from the construction I'll give you, it's clear that there is a finite spectrum with a map Vn plus 1 to the In plus 1 from this guy shifted by some degree that you can compute. It's In plus 1 times the degree of Vn plus 1, of course. Inducing Vn plus 1 to the In plus 1 on mu homology. And again, technically, if the exponents are big, this is not very well defined. I'm saying it's a representative for this class, the n plus 1 to the En plus 1. And which is, sorry, I also should say, which is an En plus 1, actually, Ln plus 1 equivalence. And that's actually a consequence of some very, very big theorems, the nilpotence and thick subcategory theorem. And you do have these working as before tells you that you have a map. And let me say that I'm just inverting Vn plus 1, because of course inverting Vn plus 1 or inverting any of its powers the same. And the theorem, sorry, not the theorem, the conjecture, which is called the telescope conjecture, says this map is an equivalence. And this conjecture has a very rich history. It has been both proven and disproven in the literature at least a couple of times. None of these were correct, of course. I think the current consensus is that this conjecture is false. And there are good theoretical reasons for why it should be false. On the other hand, these good theoretical reasons seem to apply also to the n equals 1 case, which is true. So I'm not exactly sure which position I should take here. It's, I think, the most important of the conjectures from the 70s that's still unsolved. And as a corollary, you'd have that X is is Ln local if and only if Vn plus 1 acts invertibly on X. But it's a corollary of the conjecture which is assumed to be false these days. So, you know, take it with a grain of salt. And okay, and I think that the last thing I want to say is why this subject is called chromatic homotopy theory. So this subject is called chromatic homotopy theory. Oh, there is actually another thing I want to say, but okay, I'll say later. Because Ln of x sees the Vn periodic part of the homotopy groups of x, at least when x is finite. Well, okay, we don't have telescope conjecture, so this is not literally true. But what is true is that the homotopy groups of Lnx modulo is V0, I0, Dn minus 1, In minus 1 are Vn periodic. So there is some power of Vn that acts invertibly. So you think of it as, so you think of this Ln tower, this called the chromatic tower, actually let me call of the chromatic tower, and x, Ln minus 1x, etc. goes to, oh, L0x, maybe I should have mentioned it's just a rationalization because V0 is P. And that's also, the telescope conjecture is also true for P equals 0, of course, for N plus 0, of course. Actually, sorry, not X, rationalized, the P completion rationalized. Sorry, very often in this subject, just assume that X is already P complete and call it a day, just to make the notation less. Yeah. And when you think of this chromatic power as splitting the homotopy groups of X in its constituent frequencies. So sort of like when you take a ray of light and you put in a prism, you get different rays, one in each its own frequency, so its own periodicity. So that's sort of what the goal of chromatic homotopy theory is. You take the constituent frequencies of your spectrum, and then you try to put them together, and that's, as I said last time, it's called the transchromatic homotopy theory. And oh God, that's even worse. Already understanding the Kn localization of a spectrum is hard. Putting them together involves understanding this piece here, and that's even worse. That's really complicated. But that's our best goal to understand the homotopy groups, or more general, the stable homotopy category. And as Nicholas was saying before I started recording, this corresponds to a filtration of the whole category of spectra. You can actually write the category of spectra as a bunch of pullbacks, which, as I hinted at, you could interpret as some kind of sheaf descent condition over a space that's sort of made like this, with open parts like this, which is the Balmer spectrum of the category of spectra. So this is some kind of descent condition for a sheaf of categories somehow. And of course, one could hope, okay, this is sort of like understanding the Zariski sheaf. And well, one of my dreams would be to write down an étal site and try to look at étal points, if you know about étal topology. But that's, well, that's literally a matter of current research. There are a few people working on things related to this, but we don't have quite a complete story yet. So I hope at least the idea of decomposing the category of spectra and its constituent frequencies is interesting. I actually should say this works for the category of finite spectra, not for the category of all spectra. And that's sort of good enough for at least, well, maybe it's not good enough, but it's already much more than we can do. So we have to not be too greedy, I guess. Okay. So this, sorry for this lecture, was perhaps a bit more vague with a lot less proofs, but I wanted to give you an idea of how these ideas of boundary localizations have evolved. I don't think it makes sense for me. Oh, no, sorry. I should actually say a different theorem, a last theorem here. So the theorem is this Meshing localization theorem, which is true even if the telescope conjecture is not proven and suspected to be false. Ln is smashing. This theorem is true, with a different proof from the one that I did today, which of course used the telescope conjecture for Ku. But it is still true. So Ln is, you can hope to understand Ln if you understand Ln of the sphere. Of course, understanding Ln of the sphere is not as easy as understanding L1. Okay, so again, I think I'm not going to start a new topic now. I hope it was at least interesting to see how these ideas grow and become more generalized and go to show what you're doing. And next time I'll start talking about Thom's spectra, Spanier-Whitehead duality, and then Thom's theorem on manifolds. Sorry, and Thiele duality first, of course. I think that will leave us very little time. By the end of the semester, I might have 1 or 2 extra lectures, I'm not sure, where I might do another, I don't know, general description of the developments of the theory instead of doing a new topic. Questions?
Yes, so I have a very vague question. So I once heard that this Morava E theory spectra, so I mean, we looked at the En tilde, not the Ens, but they are supposed to be somehow also primes.
Yeah, no, okay. So first of all, since you've heard about Morava E theory, I should mention that nothing I've written is actually related to Morava E theory, and just these are called Johnson-Wilson theories, and they happen to have the same Bousfield class of the Morava E theory. So that, and since they're quicker to define, that's what I'm using. But Morava E theories are, of course, a lot more canonical. When I say that there is a more canonical way of describing Ln, I was referring to Morava E theories, which take a while, that take some arithmetic geometry to define. So I'm not going to do, but Morava E theories, to answer your question actually, which is more about Ln, that En really, is not a prime, is more like the complete local ring at the prime. If you want, the analog of the prime would be this Kn theories here, that I define. Okay, Kn tilde actually is literally the sum of a bunch of I think 0 to Pn minus 1 S2I K, the spectrum called Kn, it splits like this. And these Kns are what are sometimes called prime fields of the stable homotopy theory, although I disagree with this assessment. I mean, they behave, so LKN actually behaves like at the completion of a prime. But Kn are not, for example, are not ring spectra. Or rather, they are E1 ring spectra, but not canonically so, and they are not commutative if n is greater than 0. So they behave more like classes in the Brouwer groups of En rather than primes.
And also, I mean, this is super vague. Are these somehow points in the Balmer spectrum?
Yes, this is known as the thick subcategory theorem. It's one of the important theorems in chromatic homotopy theory, and the points of Balmer spectrums depend on exactly 2 parameters, P and N. And they are exactly, the P and N is the one here, except for N equals 0 when there is no P because it's rationalization.
Yeah.
N equals 0, you have only 1 point. So in fact, the space, the Balmer spectrum of the sphere, actually, I think you have like one point. This is kind of a generic point at 0, and then you have a chain of points going closer and closer points, and so this is like HQ. Here we have K1, K2, etc. One for each prime, until they arrive at something that's sometimes called K infinity, but you know under a different name. It's just HFP, which is the closed point. It's sort of the residue field. This is not super important. I mean, it's important to make the Balmer spectrum a quasi-compact topological space, but it's not important for the description of the opens, because the opens are all, there is no open that contains only HFP.
Okay.
Sorry, no, these are the closed. Yeah. I mean, there is no quasi-compact open whose complement is HFP. If you want, the complement of HFP is not quasi-compact. So for the description of the descent statement, it's not very relevant. But okay, and the topology here is complicated. This is where the transchromatic phenomena happen. Also, when you try to glue different primes, how do this Heidstock? But we understand this picture quite well, actually, I should say. The topological structure here is quite explicit.
Cool, thanks.
Other questions? I should also perhaps say that there is another important conjecture called the chromatic splitting conjecture. That's essentially saying that this pullback is stupid. You can write these as essentially some kind of sums of these and, sorry, these and the fiber, as sums of these and the fiber of this map. So this will tell you that ln of x is the sum of the LKIs. And people believe that this is, after non-canonically so, and people believe in the truth of this statement. It's been verified for low degrees. But I'm not sure I'm not sure what I believe in, honestly, in these conjectures. So it's kind of a weird conjecture. The conjecture precisely says that there is a map like this making the direct square commute. Other questions? Yes, no, okay. Okay, so see you on Thursday and we'll do something a lot more concrete. But again, I hope this was interesting anyway. Let me stop the recording.